So last time we saw that if A has very small singular values and we apply the pseudo-inverse in the presence of noise, we can have some very unstable performance. But today I want to talk about some ways to fix least squares to make it more stable in this kind of context. To set this up, just like before, we're going to assume we have observations y equals ax plus e, where A is an m by n matrix and E represents some kind of perturbation. The matrix A, we're going to assume has an SVD given by U sigma V transpose. And just to recall what the structure of this SVD is, we're assuming that U has R columns in Rm. Sigma is an R by R diagonal matrix, and V transpose is going to be an R by N matrix with rows given by V1 transpose up to VR transpose. Now, one thing we didn't emphasize before, but that is carefully treated in the notes, is that we can also write this matrix product U sigma V transpose as the sum of rank 1 matrices given by sigma R UR VR transpose. And this summation form is a particularly useful way of writing the SVD when we're thinking about least squares and stability. So one benefit is that it gives us a very simple form for the pseudo-inverse, which is just that the pseudo-inverse of A can be written as the sum of 1 over sigma R times VR UR transpose. And the least square solution is then simply given by taking that matrix and applying it to y. Now, if we look at this formula, what we actually see is this UR transpose y term, and this is really just the inner product between y and UR. And so we can really think of the least squares recovery as being a weighted combination of the columns VR, and the weights are determined by the inner product between the UR and our measurements y. And this really illustrates exactly where the problem arises. So we see that if y has any correlation with UR corresponding to very small values of sigma r, those weights can really blow up. And this is really the problem. But this also suggests a very simple solution to the problem, which is simply to truncate our SVD. So we can just truncate this sum, leaving out any of the terms where sigma r is too small, and so 1 over sigma r is too big. Of course, there's going to be a bit of a balancing act in terms of how much we want to truncate, as we'll see in a little bit. But just to make this idea more concrete, we're going to form an approximation A prime to A that simply is exactly what we had before, but only sums up to capital R prime. And then we'll form the pseudo-inverse of A prime, which is just this truncated sum. And the truncated pseudo-inverse is simply applying A prime pseudo-inverse to Y, which gives us this truncated version of the sum that we had before. So when we do this truncation, how good is the reconstruction going to be? To answer this question, we might want to compare this x hat trunk that we're forming to the reconstruction that we would have gotten by applying the pseudo-inverse of A to the clean measurements, getting x hat clean. This is sort of the best case reconstruction we could expect, given that we're observing x through this matrix A. And if we just write out the difference between x hat trunk and x hat clean, we can express it in terms of the pseudo-inverse of A prime applied to y and A pseudo-inverse times ax. And recalling that y is equal to ax plus e, we can expand this out as follows. And now if we collect all the terms involving x in one side and isolate the term involving e on the other, we see that the error that we're going to get here is controlled by two factors. One involves the difference between the pseudo-inverse of A prime and the pseudo-inverse of A applied to ax, and the other one involves the pseudo-inverse of A prime applied to E. And we can think of these two terms as corresponding to fundamentally different phenomena. The first one is an approximation error that results from the fact that we're using this approximate pseudo-inverse, and the second term is just our noise error. So first let's look at the approximation error term. This approximation error, when you think about it, boils down to the difference between the pseudo-inverse of A prime and A, which is entirely dictated by the terms that A prime leaves out from A. So this error is just given by the sum from R equals R prime plus 1 to capital R of the terms that we would have included in the pseudo-inverse, which we can write as follows. Now, if we express A times X in terms of the SVD as the sum from J equals 1 to R of sigma J times the inner product between X and Vj times Uj, then we can rewrite this term as follows. Now, if we simply rearrange this using linearity by pulling this sum outside of this outer inner product, then what we're left with is the sum from j equals 1 to r of sigma j times the inner product. These are all just constants, times the inner product of uj with ur. Now, this is equal to 0 unless j is equal to r. And when j is equal to r, this inner product uj ur is equal to 1. And so this entire sum simplifies to simply sigma r times the inner product of x with VR. And when we plug that in, we have a much simpler expression now. So if we look at this sum that we're left with, we have a 1 over sigma r times sigma r. That cancels out. And we have this simple expression, the sum from capital R prime plus 1 to r of minus the inner product of x with VR times VR. We can also write out the noise error as a weighted combination of the VRs, where now the weights are determined by the inner product of E with UR. And then using this, we can look at the overall norm of the error. And what we notice is that the noise error term involves the singular vectors corresponding to r equals 1 up to capital R prime. And the approximation error terms only involves the singular vectors from r prime plus 1 up to capital R. And these are orthogonal, so that means that the noise error and the approximation error are orthogonal. And so to compute the norm of these two vectors, we can use Pythagoras, and this squared error is the sum of the squared errors of the two different terms. And because we're expressing them in terms of an orthonormal basis, the norm of the error is just going to be given by the sum of the squares of these coefficients that were used. So the noise error term looks much like what we had before. As before, we can say that the worst case for the noise error is going to be determined by 1 over sigma r prime squared, where r prime corresponds to the smallest singular value that we're using in our reconstruction. But if r prime is less than r, this can represent a big improvement. Of course, this comes at some cost in terms of the approximation error. We're losing the portion of x that lives in the span of the singular vectors from r prime plus 1 up to r. But if sigma r is very, very small in this range, there's probably not much we can do about this. This information is going to be very hard to tease out from the noise. Now, the truncated SVD is a very effective way of stabilizing the least squares problem. Another equally effective approach that has some other advantages that we'll talk about in a little bit is called Tikhonov regularization. The approach in Tikhonov regularization is sort of inspired by thinking about least squares as an optimization problem. And you'll recall that we actually talked about two different optimization problems that gave rise to the least squares solution. The first was to minimize overall x and Rn, the L2 norm squared of y minus ax. And this we motivated in the context when A was an overdetermined system and we had some potentially noise in our measurements and wanted to minimize the norm of the residual. Now, another optimization problem that actually gave rise to the same solution was to say, let's minimize overall x and Rn, the L2 norm of x squared subject to y equals ax. So this is when A is underdetermined, and there are many possible x that we could pick from, and we want to pick the one that has smallest norm. Now, the approach in Tikhonov regularization, or just regularized least squares, is really to consider a blend between these two approaches. So when A is maybe still overdetermined, but has really small singular values, it's sort of in this in-between land where it is technically overdetermined, but it's very close to maybe being an underdetermined system, you could imagine, because you have these very small singular values that if you ignored, maybe all of a sudden it would be underdetermined. Now, in this case, you could sort of think about constructing a combination between these two different objective function terms and say, well, we want to minimize the norm of y minus ax squared, but we also don't want the norm of x to grow too large. So we'll add an additional term that's delta times the L2 norm of x squared, where delta here just represents a free parameter that the user is going to set in some manner. This is going to control the amount of regularization that happens. In the homework, you're actually going to show that the solution to this problem in terms of the SVD is just given by v times sigma squared plus delta I inverse times sigma u transpose y. So notice that if delta was 0, this would just reduce to the previous least squares solution, but if delta is somewhat large, this could be quite different. One of the advantages that I had alluded to of Tikhonov regularization is that unlike the truncated SVD, which can only be computed by first computing the SVD of A, you can also write a different closed form expression for the Tikhonov regularized least squares solution, which is as a solution to a system of equations, specifically A transpose A plus delta I inverse times A transpose Y. So an interpretation here of what's going on is that A transpose A might be very close to not being invertible, but by adding delta times the identity, we guarantee that this is always going to be nicely invertible. In fact, you can also write this in an equivalent form, something you'll show on the homework, A transpose times A transpose plus delta times the identity inverse times Y. So either of these formulas is valid, and you can always use either of these. We'll see in a little bit why it might be useful to have this explicit formula as opposed to having to compute the SVD. Just as was the case with the truncated SVD, we can also write the solution to the Tikhonov regularized least squares as a weighted combination of the singular vectors VR. So recall that the least squares solution gave us the weights 1 over sigma r times the inner product of y with ur. In the Tikhonov regularized solution, we have a similar formula, but rather than 1 over sigma r out front, we have sigma r over sigma r squared plus delta. This is just re-expressing the formula I just wrote in matrix notation previously. And this really highlights the difference between the least squares solution, the truncated SVD, and Tikhonov regularization. So notice that if sigma r is much bigger than delta, we can essentially ignore delta, and this expression is approximately 1 over sigma r, just like in least squares. So when we have large singular values and delta is small, then we're doing something very close to least squares. But if sigma r is much smaller than delta, so if we have some singular values that are much smaller than delta, this expression is now essentially going to be very close to 0. And so what we're doing here is something very similar to the truncated SVD, but it's maybe slightly softer. So rather than picking a hard cutoff, r prime, to set all of the singular values to 0, we gradually dampen their influence on the recovery as they get closer to 0. Just like with the truncated SVD, you can do a very similar kind of noise analysis for Tikhonov regularization. It's a very similar behavior, and in general, these two methods behave very similarly in practice. The main reason to choose one over another is typically computational. Before we move on to start talking a bit more about computation, I'd like to first talk about one more way in which the SVD can help us to think about what least squares is doing. Specifically, another way to think about least squares is from a geometric perspective. So let's consider a particular problem that arises very commonly in signal processing. This is a problem where we have a vector x that lives in Rm and a subspace T that's just the span of n columns, A1 up to An, where A, N are vectors in Rm. And n is less than m, so this represents a subspace of the full m-dimensional space. And we can think of T as being some sort of signal model, and we have some vector x, and we want to think about maybe denoising x by finding a good representation of x, but one that lives inside of this subspace T. So a very natural question that you might ask is, well, what is the closest point in T to our vector x? And if you think about this for a little bit, you realize you can write this down as an optimization problem that says, well, let's take x and minimize over all y in Rm the norm of x minus y, subject to the constraint that y lives in this subspace T. Now, this might look a little strange until you realize that when we say that y lives in T, all that means is that y can be written as a linear combination of these vectors an, or in matrix form that y can be expressed as a times alpha for some vector alpha in Rn. So that means that rather than having the constraint that y lives in T, we could equivalently just pose this as a search over the coefficients alpha, in which case our problem becomes to minimize over all alpha in Rn the L2 norm squared of x minus a times alpha. And other than the fact that we're used to having x be y and alpha be x, other than this small notational change, this is exactly the least squares problem we've been considering for several weeks now. And we know the solution. So we know that alpha hat is going to be given by v times sigma inverse u transpose x, and x hat is just a times alpha hat, or expressing that in terms of the SVD, we have U sigma V transpose times V sigma inverse U transpose X. And we see that we have V transpose V, which is just the identity. So that gives us U times sigma inverse U transpose X. And the sigma and sigma inverse become the identity, and we're left with just UU transpose X. So the closest point in T to X is X hat, given by U times U transpose X. So one more thing to say about this solution. So if we look at the difference between X and X hat, we can think of this vector representing the error when we approximate X as living in T, this vector X minus X hat. It obeys certain special properties that are sort of obvious in this two-dimensional case, so I have indicated that this error is orthogonal to T. And this turns out to be a general property that's easy to show. So for any vector Y in this subspace T, you can show that the inner product between this approximation error term, X hat minus X, and Y will always be equal to 0 just by expanding this out. So we have X hat minus X is UU transpose X minus X, and since Y is in T, we can write it as U sigma V transpose alpha for some set of coefficients alpha. Now if we just expand this out, the UU transpose X term gives us an inner product that looks like alpha transpose V sigma U transpose UU transpose X, and the minus X term gives us a minus alpha transpose V sigma U transpose X. And now we realize that U transpose U in the first term is equal to the identity, and so we have alpha transpose V sigma U transpose X minus alpha transpose V sigma U transpose X, which is just 0, which is exactly what we wanted to show. So this fact that the approximation error is always orthogonal to the subspace is sometimes called the orthogonality principle. And this also motivates the terminology that we think of X hat as being the orthogonal projection of X onto T. So you may encounter this terminology or have seen it before, and it's referred to as the orthogonal projection precisely because of this orthogonality property. So next time we're going to talk about how to actually compute least square solutions, especially when the problem sizes get really large.